Okay, so guys, it's recording now. This is our third advanced topics. This is for calorimetry, as I said a moment ago. It's you do already know everything that you need in order to answer these questions, but here's the idea. In the regular class, if this is a system, we've only dealt with half of a system. What do I mean? Half of the system is gaining heat, and the other half of the system is losing heat. And there's a movement from the part that's losing heat to the part that's gaining heat. Now, in the regular class, we've either dealt with just the part that's gaining energy or the part that's losing energy. We haven't considered the system as a whole thing. It's, of course, a little bit more complicated, but hopefully it won't be that bad. I will say this is usually the topic students, it's a little involved. It gets messy mathematically, so it's not always a student favorite, but it's not that bad. And there's abundant partial credit. Now, how do I unite these two parts of the system? Well, let me write this a little bit larger. We say the following, and we've said it right along. We haven't made a secret of this. All of the energy lost by one part of the system is exactly equal to the amount of energy gained by the other part of the system. Now, Q, we know, is one of three equations. Q is either mc delta T, Q is either, or MHF, or Q is equal to MHV. So the idea is, once we decide what's happening in the system, we can substitute the Q equation into each of the Q's. So for example, in this one, in example number 1, we have a situation where both objects, oh, thank you so much, my friend. See ya. We had a visitor, yay, Shayla. I was saying, when we look in this first example here, it turns out I have a metal cube and I have a sample of water. They both change temperature. They both change temperature here. So because they both change temperature, we're going to be using this equation twice. Once for the side that's lost, and once for the side that's gained. But more about that in a moment. I want this to be totally clear, so I made a little diagram, a before and an after. And it says we have a 135 gram sample of metal. So why don't we identify that? That's the size of this cube of metal. I'll leave out the units. It's at 110 degrees initially. So that's what we mean here by TI. That's the initial temperature. 110. Let's actually make that 0.0 because we measured it on a typical thermometer. In a beaker of 200 grams of water. So the 200 grams of water is the other object. It's the mass of the water, 200 grams of water. It's at 25.0 degrees Celsius. That's its initial temperature, 25.0. Now, what are they asking for? Oh, it says, what is the specific heat capacity of the metal? So we know 5 of these. We do not know this. We're going to call that, that's what we're solving for in the problem. Do we know the specific heat of water? It's a liquid? Yes, we do. Indeed, 4.18. Okay. As I said, there's nothing crazy going on here. Now we drop it in, and when we drop it in, we have heat transfer. Of course, the heat transfer stops once everything is the same temperature. So the final temperature of the water and the cube together is 27.3. Okay. So let us set this up. I know that the metal cube is our heat loser. So let me actually write this. That's the metal. The metal is losing energy to the water. Since I know that the metal changing its temperature from 110 down to 27.3, I'm going to substitute this equation in here. So it's negative Q loss. I'm gonna include the negative. I'm gonna say something about that. I'm just gonna be super correct. I have a negative mc delta T. So I have negative mass of the metal, specific heat of the metal, and the change in temperature of the metal. Now, I need to expand that a little bit. I can do it this way. I'll just write delta T, that's fine. And I also know that the water's changing its temperature as well. It's going from 25 up to 27. So I'm also going to plug in the same equation on the water side, on the gain side. M of water times specific heat of water times the change in temperature of water. Okay, cool. Let's substitute in our values. Oh, the mass of the metal is 135.0. Specific heat of the metal, we don't know. We call that X. The change in temperature of the metal, well, remember, guys, delta T is equal to the final temperature minus the initial temperature. So it is 27.3 final minus the original 110. So I believe that is 82.7. A negative 82.7. But guys, that's why we have the negative out in front. The negative takes care of the negative change in temperature. So truthfully, you can just ignore all the negatives and just assume it'll come out positive. For our purposes, that's fine. What's happening on the water side? Well, the mass of the water is 200 grams. Specific heat of water is 4.18. And the change in temperature, well, again, final minus initial, 27.3 minus, oh good, we have half our time left, that's wonderful, minus 25.0. So on the water side, the water only changes by 2.3 degrees. A little sloppy, sorry about the breaking up there. Let's do our math. So on the one side, I'm going to clean this up. Let me get rid of that, so a little more spice. So on the metal side, we have 135 times 82.7 x. So we have 11165x. On the other side, I have 2 hundo times 4.18 times 2.3. So I have 19228. 19228. I'm going to solve for x. Divide both sides by 11165. 11165. 11165. So we have, let me try that again, sorry guys. 19228. I can't do this. 11. Oh, that's what I did. Sorry. 1922, I'm live. Divided by 11165. Sorry guys. 1.7. So the specific heat capacity of that metal has to be 1.7. Good Sir Goodstein just pointed out a mistake that I made. This should have been 1922.8, and so it's not 1.7, it's 0.17 joules gram degree Celsius, which is an appropriate specific heat for a metal. We're back. Okay. As I said, in these kind of problems, you should always set things up this way. Consider what part of the system is losing energy in heat transfer and what side is gaining energy during heat transfer. Now, notice this one is a little spicier in that one part is changing temperature, but the other part is not. Let's read this together. We have a 10-gram sample of ethanol is poured into a 2-gram sample of ice at 0. So let's imagine this. We have an ice cube originally, like so. We said that the mass of the ice cube, the mass of ice, mice, look guys, that's fun. The mass of ice is 2 grams. It's originally at 0. That's its initial temperature is at 0 degrees Celsius. And what we did is we just poured a little bit of ethanol, like this. Maybe like a little pan here, like so. Now, what happens is this. As a result of the heat transfer, now the heat transfer, of course, we're going to see that this must be the heat transfer because the ice cube melts. It changes to water at 0. So if you imagine this, if we still have our little tray over here, we still have that ethanol, but we're going to have liquid water that's mixed into it. It melted. But of course, what sometimes surprises students is that you can have liquid water at 0. So the temperature didn't change for the water, but it did change for the water at 0, yes. Yes, okay. Given the fact that the specific heat capacity of ethanol is 2.4, determine the initial temperature of the ethanol. All right. So we know that it's the ethanol that has to be the source of energy. Ethanol is the source of energy. The ice cube is gaining energy. Ice, ice, baby. Now, notice the ethanol has to be changing in its temperature. We don't know what the initial temperature of the ethanol was, but it had to be transferring energy to the ice. So we know the ethanol needs the heat change formula, because we've paid attention. M times C times delta T.
Egg salad.
Egg salad. Wonderful. Delicious egg salad. Now, guys, on the other side, we can't use this equation for melting ice. What equation would we use? MHF. We have to use MHF for the ice, because the ice melted. Let's plug our values in. It's a machine, as I mentioned a moment ago. It's a sample, a 10-gram sample of ethanol. And the specific heat, we told you here, was 2.4. Now, we're going to solve for the change. We're just going to first find out what the change in temperature is. We're going to solve for the change in temperature for the ethanol. The amount of energy in the, it's a small ice cube, it's 2 grams, 2.0. And as you guys, I'm sure, can tell me, the specific heat of water, the heat of fusion of water is? Say it, Isabel.
I don't know if it's
334. Okay. Yes, nice. A little support there. Let's do the math, guys, as they say. So we have, that's mental math even I can do, guys. That's 668 on the right side. Oh, and that's mental math I can do as well. 10 times, that is 24 delta T, and that's negative because it's a negative change in temperature. So I need to solve for delta T, and delta T, divide both sides by negative 24, negative 24. So we have 668 divided by 24 is equal to 27.8. That's going to be a negative 27.8. So very quickly, change in temperature is equal to the final temperature minus the initial temperature. If the final temperature is 0, and we're solving for the initial temperature, and this is a negative 27.8, so then I'll have to settle this. We're running out of time right here, my friends, so I have to say goodbye. There's going to be a part 2.
We're back.